Okay, now we come to multiple mass systems, multi-mass systems. That is, we have more than one mass. And what we do is we just write F equals ma for each mass. Let's say that this is one mass. There is a spring between them. This is a second mass. And let's say that these are like trailers or trains or something. Okay. Let's say this is M1, this is M2. Let's say that there is a force here. Think about it as a locomotive and a wagon that is pulled by the locomotive. So the coordinate is x1, the second coordinate is x2. We would like to find out equation of motion, well, for all systems and possibly the transfer functions. There are transfer functions because there are two displacements here. The method is the same. It is draw FBD for each mass and then write F equals ma for each mass, basically. Okay. So for M2, for example, oh, what happened? Now, there are two coordinates, obviously. Again, the same thing, we can do the same. Let's say this is k x1 in this direction, k x2 in that direction. If you consider this for the second mass, this is M2. For the second mass, if we fix the coordinate 2 and move x1 in the positive direction, the spring force is going to be kx1 towards the right? And if you fix x1 and move x2, the spring force is going to be k times x2 towards the left in opposite directions. And these are the spring forces coming because of x1 and x2. It's not easy to write, x1 minus x2 directly. So you can decompose it into two parts like this. Whereas for M1, you will have, what will you have? Kx1 will be in this direction. Kx2 will be in this direction. And there is an F, external F. These are the external forces. Supposedly this is unequal, okay, like this. This is M1, X1, double that. Now here, what we do is, we fix X2. If you move X1 only, the spring force will be towards the left. If you fix X1 and move X2, the spring force on M1 would be towards the right. So this is as we draw it. So the summation of forces is K x1 minus x2 is equal to M2 x2 double dot. And here you have K x2 minus x1 plus f of t is M1 x1 double dot. Right? Here we are summing up forces in the positive direction like this. So we have two equations for M1 and M2. Okay, 2x. Sorry, this is wrong. There is no k1 or k2, it is just k. kx1 minus kx2. And here it is k, 0. Okay. So we have two second order differential equations that describe this system. We might want to write this in terms of x and f if you like. For example, use s in terms of d by dt, in which case you will get m1 s squared plus k, let's say x1 plus, sorry, minus k x2 is equal to f, and m2 s squared plus k x2 minus k x1 equals 0, from which you can actually solve for the necessary transfer function. For example, if you want the transfer function, the possible transfer functions are as follows. You might have x1 over f or x2 over f, right? What does this mean? It means the effect of f on x1 or effect of x on f2. Okay. So, for example, in order to do this, we can use, let's say this is 1, this is 2. From 2, we can get something like this. So these k-squares cancelled. There is an s here. Okay, a lot of mistakes. This is s to the 4. This is s squared. But these k-squares cancel each other. So x1 over f of s is going to be as follows, and 2s squared plus k divided by s squared and 1 and 2, 2. For example, okay, I will leave it as an exercise for you to find x2 over f. It is quite easy if you follow the same steps. Okay, I'm not going to do it. This shows us the effect of the force on x1, which is here. The effect of this force on x1, how it causes the vibrations in x1. Okay, it's a bit complicated, obviously. It means something, but what it means, I'm not going to explain it at this moment. It's a bit complicated, but it is understandable if you think about it. Well, if you have enough knowledge. So we have, as we see, we can derive the transfer function for this system as follows. Are there any questions about this? Another multi-degree of freedom, multi-mass system is the car suspension system, let's say. Let's say that...
Hocam, may I ask something?
Sure.
So, like, what exactly this transfer function tells us, and like, what is the help of it in our systems?
Well, actually, we will see how it helps us. We will eventually try to represent our systems in transfer functions so that we can put them in blocks like this, where f is the input, let's say, and let's say x1 is the output, and there is the transfer function, which we will call g of s, which is this thing, okay? And we will combine these blocks together in order to obtain a general system, especially in specific a feedback system. A feedback system is made up of many blocks like this. There is the controller block, there is the system block, there is the actuator block, there is the sensor block, etc. We combine them and then derive the general equation for the system.
So for the S, what are we going to input?
Huh?
Like before it was t, so it is time. So now S is equal to d over dt.
We still input a time function. This is an analysis tool. Okay. Basically, what we do is we take the Laplace transform of the input and then multiply it with the system transfer function. We just use the same input, but we use the Laplace transform form of it. Okay, this is an analysis tool. Of course, we don't do anything out of the ordinary when we use S. It is just a tool for analysis. Okay?
Okay, hocam. Thank you.
We will understand it better. I'm just trying to show it without much theory at this point. And it's at this point kind of understandable without the theory. So you have a car suspension system. Let's say you have a car mass M2, let's say. This is actually a quarter of a car. Let's say the car's 1/4 of the car is carried by a suspension system like this, okay, in which there is a, sorry. This is M1. This is supposedly the wheel of the car, so that it is also modeled, okay? And the wheel has a certain elasticity, so we model it like this. And this thing is on a bumpy road like this one, okay? The road is not very smooth. And there's a reference point, and this is R of t, the input. This is K, the stiffness of the wheel, Kw. This is Ks, the shock absorber. This is B. So this part is the shock absorber. Okay, and the coordinates is the motion of the wheel is x of t, and the motion of the car is y of t. Okay, 1/4 of the car at least. And this whole thing moves with a velocity of v, but we are not interested in that. We are interested in the vertical vibrations of this thing, okay? Not in the horizontal motion. The suspension system is about the vertical motions. So there might be input is this is the input, and usually this is the output. The vibrations of the car is the output, and the wheel, the bumpiness of the road is the input, as you can see. There is gravity here, but we are not going to consider it. We are not going to take it into account. If you have taken 301, you remember that we kind of neglect gravity and assume that the static deflection of the springs takes care of it. So gravity will be ignored here, okay, for our purposes.
Hojam, can you explain what's the function RT near the wheel?
RT. That is the bumpiness. There is the road. Road is not very smooth, let's say. You are going on a bumpy road, okay? And yes. This straight line is our reference point. And R of t is the difference, the bumpiness of the road measured from the reference point. Do you understand?
Yes, Hojam, thank you.
Yeah. So we have to draw the free body diagrams and etc. and all these. So the free body diagrams are as follows. You have for M2, you have the spring force, the damping force, let's say. This is Y. Is equal to, let's say, oh, sorry, not like that. And 2y double that. And for the first M1, you have the Fs and Fp like this. There is the Fw. This is equal to M1 x double dot. Again, we do the same thing. I didn't draw, x1 and x2 or x and y separately. Now the spring force Fs is downwards, as we see. This will be when you move y upwards and keep, this is x, by the way, x without any motion. This will be k times y minus x, because the spring force acting on M2 Fs is downwards. Now, if you move y upwards, the force will be downwards, so it is ky downwards, that's correct. If you move x upwards, on the other hand, without moving y, the spring force will be downwards on M2, so it is ky xy minus x will be the correct expression. And the same is true for M1. If you check it out, it will be ky minus x will be the correct force acting in the upward direction.
Hojam, question.
Yes.
On mass 1, the force is acting like from the road, like upwards. So shouldn't the forces from Ks and like the damper and the spring, shouldn't it be downwards on mass 1 instead of upwards?
No, we assume the direction here. Okay, we assume that the direction of this force is downwards. For on M2, let's say. And
Okay.
for M1, we assume that Fs is upwards. And
Okay.
we write the equations accordingly.
Okay.
Do you understand?
Thank you.
Mhm. And similarly, Fb is written by dot minus x dot. And Fw, the wheel force, is similarly Kw r minus x. Okay, r is the input. So we just write our equations now. I try to, write it in a compact form. Summation of forces equals MA for M1 and M2. So summation of forces on M1 is the spring force plus just a second. Spring force plus the damping force. If we are looking at M1, Fb plus Fw will be equal to M1x1 double dot, which will be Fs is ky minus x plus y dot minus x dot plus Fw is kw r minus x is equal to 1x1 double dot. And for M2, minus fs is going to be k. Sorry. I just mixed it up. I do things automatically, and that makes it. Of course, I'm not using x2 and x1 here. I'm using y. Okay, I'm using y here, right? Okay. Fs is minus k. It was what? Y minus x minus b y dot minus x dot is equal to m2 y double dot. So if we write these equations together, rearrange them, and then write them together, you will get m1 x double dot plus b So these are two coupled differential equations, as you see. Two coupled differential equations, and as you see, r of t is our input and y of t will be our output. Okay. We can derive the transfer functions from here, taking the using the S operator instead of derivative, but it will be a long process. I don't know, it's worth it trying it here, but it can be done. One thing I want you to note is the following. This is the equation for let me draw it, for the x coordinate, and this is the equation for the y coordinate. The highest derivative term is x here, and the highest derivative term is y in the second equation, as you see. Look at this. Let's look at the x terms. Okay, this one is the x term, this one is the x term, this one is the x term, and here you have an x term. And for the y terms, you have this is y, this is y, this is y. Yes. So in these equations, the ones I have underlined are all positive coefficients, have all positive coefficients. There are some negative things, but they don't belong to the x terms, neither to x double dot, nor to x dot, nor to x or x. Here you have, in the y equation, all the y terms are positive. In the x equation, all the x terms are positive. And that is not coincidental, okay? It basically shows you that this system is a stable system. Well, it doesn't exactly show that, but it is something that you should be checking when you derive your equations. If the x equation has negative terms in it, negative x terms in it, you should be suspicious, because it means that the system it means that the system is unstable, basically. And usually it means that probably you have made a mistake in deriving the equations. The most common mistake in deriving these equations is the sign errors. You put positive instead of negative, negative instead of positive. So you should be aware of this fact that for most systems, the x equation contains only positive x terms and possibly other negative terms. The y equation contains only positive y terms and possibly some negative other terms. But you should be very careful about the writing negative terms in your equation, positive and negative. So basically, these are the things we should be considering. We should be paying attention to. Okay. Are there any questions up to this point?
Hocam,
Yes.
so like to systems stay in the place, like isn't M2 needs to be like stable to somewhere or something?
Well, this is
So
a
it is not moving. Like M2 needs to be stable so that M1 and M1 and the wheel can move without yani disrupt.
stable means that the vibrations or the oscillations of the system eventually die out. Okay, if there is no steady input. So if you start from an operating point and well, let's say that there is no input to the system and you just give initial conditions to M1 and M2, they will eventually, the oscillations are going to die out. That's what stable means. And the car suspension system, the model of the car suspension system is a stable system because the oscillations of such a system without any input are going to die out and the system will be in a, let's say, without any motion, will be left without any motion. Whereas, for example, if you have a pendulum, like inverted pendulum like this one, the oscillations, if you disturb this pendulum, it is going to fall down, okay? This is unstable.
Uh, Actually, I try to say like, isn't just the M1, the mass M1 is the one that is moving? Like there is no YT that I'm trying to say. Because if they are both, yani ikisi de aynı anda hareket ediyorsa hocam bunu işte bu pet'te sabit tutan veya orada hareket edebilmesine devam etmesini sağlayan şey ne? Sağa sola yıkılmadan, şey yapmadan. Yani sonuçta sadece M1 hareket edebilirmiş gibi hayal edebildim de şeyi hayal edemedim. İkisi birden hareket ederken.
No, we are, first of all, we are just considering the vertical motion. We somehow assume that the horizontal motions are constrained. Okay, this is just 1/4 of a car. The other parts of the car constrain it from not falling down, let's say. Okay, if you think about it that way. We are assuming that the motion is only upwards and downwards, only vertical. There is no horizontal motion. Or the horizontal motion is not of interest to us. Okay?
Okay.
Hocam, the definition of a stable system would be that the system comes back to its initial position as how it started.
As long as there is no input, if you disturb the system, it comes back to its original equilibrium. Yes, that's stable. That is the one definition of stability.
Okay, thank you.
Or if you have a bounded input, you get a bounded output. That's another definition. There are many definitions, but these are the most common things. Okay.
Okay.
There are some hands raised here, Fatih and Emre. I guess you are Fatih, have a question.
Hocam, you answered my question before.
Okay. So we have very little time left. Actually, I guess that's enough for today. We will continue on Thursday. But let me just stop the recording.